Hello and welcome. Today I'm going to talk about the architecture, the data flow and the physical design implications of 3D-ICs for DNN accelerators. My name is Moritz Joseph, I'm from RWTH Aachen University, and this is a collaborative work together with Georgia Institute of Technology. If you want to accelerate DNN workloads, you have to take a look at the prevalent compute patterns. These are convolutions that yield matrix-matrix multiplications. Matrix-matrix multiplications can easily be parallelized using the atomic multiply and accumulate operations that you find in these mathematical scheme. In conventional 2D ICs, this is done, for instance, using 2D systolic arrays that yield spatial parallelism. So you have the input matrix coming from the left and the top, and you have multiply and accumulate MAC units within your array that do the atomic matrix-matrix multiplication operations, and you have those spatially spread out to do this in parallel. If you take a look at realistic examples for instance at image processing, what you will see is that you easily get 7 or more levels of parallelism. But you have to map those to a 2D space. So the question arises, how do we map these millions of computations over this limited compute and memory resources? There are different approaches to that. 3 are on the level of ordering those for loops, which are not that relevant in this part, but 2 are in terms of mapping. So you can do either a spatial mapping or a temporal mapping. So in the spatial mapping, you map the operations to these parallel units, and in the temporal mapping, you map them sequentially to the same unit. And this is what we call a data flow. And the important observation that we make here is that even for very small examples, like a convolution with a batch size of 1, you already have a 6-dimensional operations, and the 2D accelerator is limited in this spatial parallelism. So what can we do to increase the spatial parallelism? One approach would be to go into the 3rd dimension. So in 3D in general, you can integrate chips either using stacking of dies, so you bring up 2 dies together here, or you can monolithically integrate them from bottom to top. And then you have to vertically interconnect them, where you can either use TSVs through Silicon Via for stacked systems or MIVs for monolithically integrated systems. And this is quite cool. So it has shown a lot of promises, for instance, higher integration density, shorter interconnect length, and also enables novel 3D architectures. But there are also key challenges like thermal limitations, the area of TSVs is large, of MIVs as well, and there's also a low yield. So 3D architectures for 3D integration enable to increase the spatial parallelism. So let's take a look at them for the use case of DNNs. And this directly leads to today's agenda. So our observation is that we have this limited spatial parallelism in 2D DNN accelerators, and we propose to go 3D. And if we take a look at existing solutions, we didn't find any true 3D architectures with the 3D topology also using 3D technology. So our solution is to propose a co-design of a 3D topology using a 3D IC and implementing a new 3D data flow. This we will analyze in terms of performance, area, power, and thermal limitations, and finally conclude, and we can show that we can achieve up to nearly 1 magnitude of performance improvement. So let's first go again through our observation that our 2D accelerators are limited in spatial parallelism, and we want to go 3D and take a look how other works tackle this issue. So the first work is from Kung et al. It is going 3D in ways that we are pipelining layers of CNN inference into a 3rd dimension. So basically you have multiple layers of your CNN, and then you can already start working on this layer with the results of the previous layer. And this is done in 3D by having 2D accelerators that are stacked in a 3D fold. And in our opinion, this is not a true 3D architecture because the systolic arrays and the data flow is still a 2D one. Then we found one work from Wang et al. About 3D CNNs, which is very application specific, but goes more into the direction of what we want to do. So here in the 3D CNN, you have a 3D compute space. So let's map this to a 3D systolic array. This is a 3D topology, but it is at the end layouted in a 2D IC. So basically it is a flattened topology, and this is limited in terms of scalability due to the length of global wires as shown here. And finally, a lot of works, this is just one example, focus on using in-memory computing for 3D stacked memory. And again, here, these are, in our opinion, not true 3D architectures because the logic die in which the accelerator is implemented is still in 2D. So this is why we argue that there are no true 3D approaches to DNN accelerators, and we want to go 3D in this work. So let's first take a look at our accelerator. And what you can see here is our whole idea of the architecture. So you still have these multiply and accumulate units that are interconnected, but now in a 3D stack here, as you can see here. And as also in the 2D case, you have input and from the left and from the top to feed the data into the array. And the output comes out at the bottom here, but only at the lowermost layer. And what you can see here is it is both a 3D topology, so your multiply and accumulate units are interconnected in a 3D fashion, but it is also layouted in a 3D IC. So let's design a data flow for this specific use case. And let's first take a look at the conventional 2D case. So in a conventional 2D topology, what you have, you input your data from left and top, and then you do an in-place reduction in your multiply and accumulate units. And there are two things that are important here. First, your reduction is done in place, so it is in the temporal dimension, and you have to skew between the rows and columns of your input to keep timing so that the input data are at the correct time at each multiply and accumulate unit. So our idea is to map these in-place reductions from the temporal to the spatial domain. And this looks like this. So let's take a look first at a single pile of max. So this is like 3 max units on top of each other. And what you can see here is that we now combine the reduction in place, still in the temporal dimension, but also separated in a spatial dimension over the 3D. So basically we have a combined 2D and 3D approach here. And also what you can see is that you need a skew between the layers of one clock cycle, which is basically just analog to the 2D case, to keep timing so that the results are at the correct MAC unit at the correct time. And well, your output comes down at the bottom layer. And if we now take a look at the whole systolic array, what you can see here is that you fed in the data from top and left. And then the first observation is now that you have skew between rows and columns as in each 2D case as well for each layer, but you also have to skew between the layers of your 3D stack. And then for the final output of your data flow looks like that your data flow from the topmost MAC unit to the bottommost MAC unit doing a reduction in the third dimension, and then they flow out at the bottom to your output SRAM as shown in the first image. And we call this a distributed output stationary data flow because it is an output stationary data flow as the output is generated in each of the MAC units, but it is distributed among 3D dies. So let's take this approach and take a look at power, performance, area, and thermal limitations. So our experimental setup looks as follows. We have proposed an analytical performance model that is validated against RTL. You can find it in the paper. And we also made an RTL implementation. For performance analysis, we swapped different workload parameters. We modeled the CNNs as matrix-matrix multiplications, and this yields the parameters m, n, and k, the outer matrix dimension m and n, and the inner matrix dimension of the product k. And we took them from typical workloads that you can see here as an example. For area analysis, we synthesized against with 50 nanometer free PDK. The power analysis was done post-synthesis using prime time PX, and for the thermal analysis, we used hotspot 6.0. So let's first take a look at the performance. And we are now going to go through all the workload parameters, and we are going to start with the inner matrix dimension k here. So on this slide, you can see the tier count on the x-axis and the speed up normalized to 2D on the y-axis for different numbers of k and different MAC sizes. And the two most important findings here is that if k is higher, you get a larger speed up. So this is what you can see here. For one color, you always see that the circle is has a higher speed up than the other two pictograms here. So basically, if you increase k, you increase your speed up versus 2D. And the second finding is that 3D is not advantageous for a small k, as shown for the green examples at the bottom. Let's take a look at the other two parameters, the M and N parameter. And here we have the Mac budget on the x-axis and the normalized speed up to 2D again on the y-axis. And you can see that different parameters of k and n are plotted here. And n and m are symmetric in terms of their influence, so we only take a look at n. And the most important finding, there are more in the paper, but the most important finding is that there's a max threshold for which 3D is worth it, and this is this n min. So you can take a look, after this max threshold, you actually get a speed up from going 3D. And this is quite cool because we could show that it is m times n. So that's a really neat formula for you to calculate for which case and which scenario it is worth going 3D. And since we already are at the influence of the Mac count, let's take a look again at those two figures and figure out what is important in terms of Mac count. And the first finding here is that 3D is only worth it for a large Mac count, and this is what you can see here. So only for a large Mac count you actually get something from going 3D, because depending on your workload parameters you will have a loss of up to 51% in terms of performance, but you can also get a performance improvement of nearly 1 magnitude. So that is really cool. And the second finding is that if m and n get larger, then you also need more max. So this is basically what you can see here, going from the green n to the purple n. So if your workload parameters and your m and n get larger, then also you need more max to actually make it worth going 3D. So that's cool. So in terms of performance, we have now seen that for large workloads and large compute resources, 3D is worth it and then gives you up to 1 magnitude of performance improvement. What about power? Well, power was quite easy. We just basically implemented it and saw that you can get between 2 and 5% power savings. So that's quite nice. But temperature is always an issue for 3D. So what do we see in terms of temperature? And here you can see for different Mac counts again, comparing the temperature of a 2D, a 3D with TSVs, and a 3D with MIVs, both for the bottom layer and the middle layers. And the bottom layer is closer to the heatsink. That's why it is separately drawn here. So the first finding is, that's quite simple, that the 3D systolic array runs hotter than the 2D one, and this is as expected, frankly spoken. The second one is, which is also as expected, that the TSV-based array runs cooler than the MIV-based one, which is due to the larger area of the TSVs. Also, the bottom layer runs cooler because it is closer to the heatsink. But the final most important result is that even for the largest Mac count and MIVs not close to the heatsink, we are still below 336 Kelvin. So we can show that it's thermally feasible to go 3D. Finally, I would like to draw your attention to area. So as I said, TSVs and MIVs require a lot of area. So naturally, your design will be larger than in 2D. But is it worth it? And to investigate this, we have drawn here the performance per area depending on the tier count for a certain workload per example. And what you can see here is that first, TSVs only offer a compelling area performance trade-off for very fast architecture like this instance here. For MIVs, the story is better. So MIVs nearly always outperform 2D ICs. As you can see, only the small example, this is not the case, but for all the other examples, they outperform them. So that is really cool. So to summarize those key findings, we have taken a look at per area, power, performance, and thermal limitations, and now what is our conclusions for all of these? And in terms of performance, we see up to 1 magnitude of speed up for large systems and large workloads. So that's clearly a data center focus here of going 3D. In terms of power, we see that we have a similar power budget than 2D, so that's also cool. 3D is better or equal, so if you want to facilitate the high performance, you will also be able to do this at a similar power budget. That's really cool. Temperature is always one of the main concerns for 3D, and we could show that it's feasible. So we keep even for the large designs below the 336 Kelvin, so our design is feasible. And in terms of area costs, as I just recently argued, it is not always worth it for TSVs, but if you use monolithic integration, your trade-off is actually quite good and you can get a decent performance upgrade. Thank you for your kind attention.